Today we're going to talk about conjugated systems, chapter 15. The first thing we want to do is we want to draw 1, 3, 5 hexatriene. So there's 6 carbons and we have 3 double bonds at carbon number 1, carbon number 3, and carbon number 5. 1, 3, 5 hexatriene. We want to construct the molecular orbitals and fill an energy diagram with the pi electrons with the bonding and anti-bonding molecular orbitals for the structure. So here we have, to do this, we have the energy that goes up here. And so that increases energy. Your lowest energy then would be here at the bottom. Now, the best way to do this is just to draw a straight line, and each one of these carbons is an sp2 orbital. So that means there's an unhybridized p orbital. And so we have sp2, sp2, sp2. So we have basically for every carbon we have an sp2 system. So then we have unhybridized p orbital. 1, 2, 3, 4, 5, 6. So we have 6. And we're going to have 6 of these. So we draw 6. Just like this. 1, 2, 3, 4, 5, 6. So we have 4. We got 2 more. Okay, so we have 6 of these. And so you have 6 carbons, you have 6 sp2 systems that are in a plane. We have an overlapping of p orbitals. So you want to count your number of pi electrons. So 1, 2, 3, 4, 5, 6. So you have 6 pi electrons. And you have 6 molecular orbitals. And so therefore you're going to have 3 bonding molecular orbitals, and you're going to have 3 anti-bonding molecular orbitals, and these are usually denoted by a star. So this one's going to be pi 1, pi 2, pi 3, and then this is going to be your line here, that everything below are molecular bonding, and everything above, because it's higher energy, are anti-bonding. And so this is called pi 4, and we star it. Pi 5, and we star it, and the star means that they're anti-bonding. So any electrons that fill in these higher anti-bonding, higher energy anti-bonding orbitals make the compound destabilized. So stable molecules tend to have these field bonding molecular orbitals. And you don't have electrons in the anti-bonding molecular orbitals. So the goal here is then we're going to focus on these pi electrons, which we have 6 pi electrons, and we're going to put those in the lowest energy and fill up from the bottom to the top. Now, what do these molecular orbitals look like? Well, these are the wave function, and these are orbitals of the probability where you're going to find your electrons. And the lowest energy will have 0 nodes, okay? So you start with this. This is a 0 node, 0 node. So you notice that these are all constructive waves of the probability where you're going to find your electrons. And the red is where you find your electrons. Now, the next energy would have 1 node. So it's just a crossover. So we're crossing over now to the bottom. And so this crossover would be, that would be a node right there. That would be a node right there because it's a crossover. You see it's a crossover? So that's 1 node. Okay, the next one, the lowest energy, would only have 2 nodes. So in order to do that, it's kind of like a little puzzle. Okay, so those are constructive. Then we're going to cross down. So there's 1 node. And then there's 2 nodes. So as you can see, this would be 1 node. and this would be 2 nodes. Okay, so the next one, now we're into the anti-bonding. See the little star? And so these are going to have 3 nodes, 4 nodes, and then 5 nodes. So we're going to have that many crossovers. So if you draw these, this is the proper way. We're going to have 1 node there, and then we're going to cross over. There's 2 nodes, and then there's 3. So you can see that's 1 node, that's 2, that's 3. Okay, and this one we have 4 nodes. So here's 1 node, there's 2, because we crossed over, 2, there's 3, and we're going to cross over again, there's 4. There's 1, there's 2, there's 3, there's 4. And then the last one we have 5 nodes, so they're pretty much all destructive, right? Crossing over. So if you count that, 1 node, 2 nodes, 3 nodes, 4 nodes, 5 nodes. Now what you do is you make little boxes for the electrons when you're dealing with molecular orbital energy diagrams. And we're dealing with 6 pi electrons. So we fill them from the lowest, and they're Hund's rule, so they're the unpaired or the paired, well, the unpaired. Yeah, they're paired. You want paired on that same energy level, and then you want them to be one going up and one going down. So there's 4, and then there's 6. So you see how they're all under the bonding molecular orbital. So 1, 3, 5 hexatriene is a very stable molecule. It has all its electrons in its bonding orbital. Now, when you're dealing with detection of UV spectroscopy, UV spectroscopy is looking at your HOMO molecular orbital and your LUMO. Okay, so the HOMO molecular orbital, let's see what that stands for. That's the highest occupied molecular orbital. And then LUMO would be your lowest unoccupied molecular orbital. So this is your LUMO. Notice it's unoccupied. There are no electrons in that molecular orbital. And then your highest occupied molecular orbital energy, highest in energy, is here. Now, what UV does is UV is transitioning an electron from your highest molecular orbital. So one of these electrons would get zapped with some energy. That's what the UV transition does. And you go from a pi, you see the pi 3, to a pi star. So a lot of times you'll see in UV you're going from a pi to pi star transition. So what you're doing is you're exciting this one electron from this HOMO, highest occupied molecular orbital, to this LUMO, lowest unoccupied molecular orbital. And this is a pi to pi star transition. Now when you do that, you get absorption. And this absorption absorbs in a certain wavelength. And the wavelength, so you think about wavelength, it's measured in length, right? And it's measured in nanometers. So 135 hexatriene will do a pi to pi star transition at 258 nanometers. So this can be detected. Now, ethene. Ethene, let's look at ethene. So we have ethene. Ethene has just 2 carbons, right? So if you look at its energy diagram here, you would just have the 2 here. That would be pi 1, and then you would have the pi starred. And this would be your bonding. Remember, you have to have as many bonding as anti-bonding molecular orbitals. So this is your line. And you would have How many pi electrons? You have 2 pi electrons. Now we fill out, this would have 0 nodes because it would be the lowest energy, and this would have 1 node. So it'd cross over there. So that would be 1 node. Okay, so when you put your electrons in, put our little boxes here, you have 2 pi electrons, and they both go here. Okay, so they're ethene, which is actually what's sprayed in tanks for like when you harvest green apples or green tomatoes. Ethene is a ripening agent that plants give off in the air to each other, and it causes things to ripen. And so actually these green apples or green tomatoes get transported to wherever they're supposed to be, and then they get sprayed by humans with ethene gas, and it causes them to ripen. But anyway, so let's talk about UV here. So if we have a UV transition, we're going to excite those electrons and excite them from a pi to a pi star. So what's happening then is this one electron here is going to get excited, and when that gets excited, that occurs at a very low frequency or low wavelengths. And I don't have that recorded, but I want to say it's less than 200 nanometers. It's less than 200 nanometers. So I want to say it's like 198 nanometers, but I don't know. But it's definitely less than 200. And the reason why, what's going on here, is you got to look at your HOMO, your highest occupied molecular orbital, with your lowest unoccupied molecular orbital. And this energy gap here is closer. Okay, this is a closer energy gap than here. So in conjugated systems, what's happening is the energy gap, so if you increase conjugation, then you are decreasing your energy gap between your HOMO and LUMO molecular orbitals. And so when you do a excitation from a pi to pi star, it takes less energy, and you end up getting longer wavelengths. So that's why 1,3,5 hexatriene, because it has more conjugation, will absorb at a longer wavelength than ethene. In fact, conjugation is exactly what happens when we get such long wavelengths that we get in the visual spectrum, the visible. So an example is beta carotene. I'm not going to draw the structure here, but you can look at it. But it has 11 conjugated double bonds. Okay, so you think 1,3 hexatriene has 3, ethene only has 1. So beta carotene, yes, that is in derivatives are in tomato. So it makes tomatoes red, and it makes oranges orange. And that's the color. So once we increase conjugation, this absorbs at 454 nanometer. So that's the visible region. So it's that increase in conjugation. And what's happening is you're actually decreasing that energy gap between your HOMO and LUMO molecular orbitals. This problem is about classifying dienes as polyenes as isolated, conjugated, or accumulated, also known as allenes. So the first thing you want to do is draw the structure. So this is cycloocta. I don't know if you can see that's D, that's E, that's F. Okay, so move that over there. Okay, so the first thing we want to do is draw cycloocta. So let's draw an octane ring. It's like a we call that a stop sign. And then you have 1,4-diene. So we can just pick 1, 2, 3, 4. So 1,4-diene. Best thing to do here is then classify the hybridization. So that carbon is sp2, sp2, sp3, sp2, sp2. This would make, because of the sp3, that would make that isolated. That's an isolated diene. Now, basically, the electrons in the conjugated system, when they're conjugated, can travel through unhybridized p orbitals. So these are in the plane, and they're above and below. And I just basically am going to erase that because, well, okay. And so when you have an sp3 system, then it blocks that conjugation. So there's no traveling of the electrons. Okay, so let's do B. Cyclooctadiene 1,3. So let's go back to drawing our stop sign. And then there's 1, there's 2, there's 3. Okay, so that's cycloocta 1,3-diene. And then let's classify the hybridization. That's an sp2 carbon, that's an sp2 carbon, that's an sp2 carbon, and that's an sp2 carbon. So in this case, it would be conjugated because they're all sp2. So this is conjugated. And each one of these carbons has an unhybridized p orbital in which these pi electrons can resonate on all atoms because there's no block, there's no sp3 atom there, so it can travel. Okay, let's do C, cyclodeca. Now when you're doing cyclodeca, a little hint, when you're trying to do these 10-member rings, kind of go like you're going to make like a cyclohexane, but don't, right? And I wonder, there we go. Okay, so now we have, let's count 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2-diene. So there's 1, 2. Okay, so here we have an sp2. This would be an sp, and this is an sp2. So if you have an sp carbon in there, that's called an alene. And that's essentially like this. It says an sp. And those are linear, and those are less stable than a conjugated system. And it's actually less stable than just an isolated system. They're higher energy, meaning they're more reactive. Okay, the next one we have cycloocta tetracene. So once again, I'm drawing the cyclooctane ring, and there's 1, there's 3, there's 5, and there's 7. Okay, so when we classify these, we got an sp2, 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 sp2. Those are conjugated. That's a conjugated polyene. Okay, D. D is, we just did D. Okay, let's do E. Cyclohexa, so 6-membered ring. 1, 3, 5. So this is benzene. And benzene is definitely conjugated. You'll see that each one of these are all sp2 hybridized. So that is definitely a conjugated system. And next chapter we'll even talk about, it's actually further classified as an aromatic compound. Okay, EF. pentatriene. So we've got 5 carbons. 1, 2, 3, 4, 5. We have 1, 2, and 4. So even though we don't have this drawn linearly, it should be drawn like this. 1, 2, 3, 4, 5. So this would be an SP. This is SP2, SP2. This is SP, SP2, and SP2. So this would actually be considered an allene. It'd actually be called an allylic allene. It would be very high energy. Okay, now we have an extra D. Is that the same thing? Cyclooctane 1357. We've already done that one. Cyclohexate, we've done that one, and we've done that one. Okay, so we're finished. So hopefully you know how to classify dienes and polyenes as isolated, conjugate, or allenes. Okay, now we're predicting the products of the following reactions. So we have allyl bromide. Allyl bromide. That's an allylic system. So you have to have an sp2, an sp2, and then this is an sp3. And this is reacted with cyclohexyl magnesium bromide. Now, we have here magnesium's plus, this makes that carbon negative, and we have an SN2 reaction. Now, just so you know, allylic bromides, right down here, allylic halides are more reactive than primary alkyl halides for SN2. And allylic halides are actually very reactive as tertiary alkyl halides in SN1. They even actually, allylic halides will actually go SN1 as well, and that's because of the resonance stability. So they do it both. They do it all. And so what's happening here is in SN2, this carbon is going after, so that's the nucleophile. This is a positive. There's the polarity there. Delta negative for the bromine and delta positive for the carbon. It's an sp3 carbon. We know that sp3 alkyl halides undergo SN2, and then so we have a backside attack and we make our new bond here. So it's just an SN2 reaction. Okay, what about B? Let's do B down here. Cyclopentadiene, and anhydrous HCl. Okay, so what happens here is this is a delta positive, and that's a delta minus. And let's just use one equivalence here. It's not specified, but we're just going to do one equivalence. So we do electrophilic addition. So these electrons here are going to go and go after the proton, because HCl is a nice acid, right? And then you put the proton there, you generate a carbocation and this chloride nucleophile. Now, if this chloride then comes and attacks at that, this is called an allylic carbocation, which is very stable, you get this product, which is an allylic chloride. And we call that 1,2 addition. Now that's kinetically, you can actually always get a 1,2 addition over 1,4. And to do that kinetically means you do it like at minus 80 degrees Celsius. You do it very cold. That's your kinetic product. Now, a thing you always have to be aware of when you're dealing with allylic cations is they can do resonance. So then we can get where, I'll redraw this one. So when you have an allylic cation, those electrons can resonate there, and then you get the plus over here. Now the chlorine then, nucleophile, can come here. And then what is that product? That product becomes there. And what is that? That's a 1 to the 2, 3, 4. It's called your 1,4 product. And that's going to be predominant at room temperature. That's going to happen at room temperature, or even if you warm something. And that's your 1,4 product, addition product. Now, the next one is, let's see if I can cut this. Okay. 2-methyl propene plus NBS and light. Okay, so let's look at that structure, that reaction. So propene is 3 carbons, and 2 is a methyl, and propene. So it's not specified here, so it's on the 1. 1, 2, 3, that's 2-methyl propene. NBS, N-bromosuccinimide. Okay, so N-bromosuccinimide is this compound here, and so that's N. This is succinimide. That's what the S stands for. B stands for bromo, and the N is because of the nitrogen here. So that's your reagent, N-bromosuccinimide. It's a little solid that you can put in your flask, and then so if you have NBS, a little bit of light, shine like a little bit of UV light on it, it generates. So whenever you see this reagent, you should just go ahead and generate a bromine radical. NBS is nice because it generates the bromine radical at low concentration and keeps the mechanism to be a free radical mechanism. And it also is controlling by picking up the the proton HBr, and limiting the amount of acid that's being produced. So NBS is a good way to keep this a free radical. So when you see NBS and HNU, you need to think, okay, this is a free radical. You can go ahead and just draw your bromine radical. Now what happens is it's going to pick up a proton. Not necessarily a proton, it's going to, yeah. It's not a proton, a hydrogen radical. So it's going to take off a hydrogen. Essentially, it's a free hydrogen because it's going to have its 1 electron there. So where does that come from? It's going to take the one that is the easiest to abstract, the one that's the lowest energy. And it's going to be a fishhook arrow because that's going to go to bromine here. So then we draw each one of these in here. And this now is a carbon radical, and HBr. Okay, so what is this? This is a intermediate, and it is called an allylic radical. So this allylic radical is actually a pretty stable radical. So this will happen. And now, we'll just draw it like that. It's going to react with NBS. You can do it like this. You can take that radical there, or you could just do BR. I say just do BR. Let's take that away. So it's going to react with Br, and you're going to get free radical. So this is going to come here. This is going to rub on there, and then that's, see the fish hook arrows? And then what you make is an allylic bromide. Of course, we can go ahead and draw our hydrogens. And you generate another bromine radical. And when you're doing these are called propagation steps, and that's how you do the mechanism. And you basically take a neutral molecule, react it with a free radical species, and you generate a free radical species and a neutral molecule. And then you come down here and you take your newly generated free radical species, in this case the allylic radical, and then you react it with a neutral species, and then you're supposed to get a neutral product with a free radical species, and that's how you know you're doing it right. So this is called allylic bromination, and this is allylic bromide. Okay, predict the products of the following reactions. Okay, so we have some more here. So furan is, you all know tetrahydrofuran. Tetrahydrofuran is furan with 4 hydrogens. So this is the furan without the 4 hydrogens. So that's furan. Plus trans. Now, I'm going to draw this differently because I just realized what type of reaction it was. And it's going to react with trans 1,2-dicyanoethylene. So obviously this is going to be a Diels-Alder. And we have a diene, which is furan. And we have a dienophile. It has some electron withdrawing groups, so it's a good dienophile. Okay, so what's happened here is these electrons, this is concerted, are going to go here. These electrons are going to go here, the pi electrons. These electrons are going to go here. So when we draw this, we draw our 6-membered ring with our new sigma bond being made, and then our new pi bond. And we got to look at the stereochemistry here. This is trans. So I'm going to draw it trans. I'm just going to make one go up and one go down. And then don't forget your bridge head right here, which we'll make in blue, goes up because it's on those 2 carbons there that are forming the new. And that is your product, your Diels-Alder adduct. Sometimes they call these an adduct. All right, let's go to the next one. E, 1,3-butadiene and bromine, water. So 1, 2, 3, 4, 1, 2, 3, bromine and water. And let me just draw this like when you're drawing your mechanisms, it's best to draw everything out. All your lone pairs, all the hydrogens. Now, let's just do one equivalent here. One equivalent. This gets polarized to delta positive, delta minus, because it's just so big. It can get polarized. And you're going to make the bromonium intermediate. Now, if you remember, this is going to be a Markovnikov product. And since you have water around, that's going to be your nucleophile. So it's going to be these electrons, and it's going to attack the more substituted carbon because of this positive three-membered ring. It's going to attack there, and it's going to open. And since you're coming in from a backside attack, it's going to be anti. So we just draw this as anti. So if we make this go up with the OH, we'll make that go back with the Br. But since there's two hydrogens, it really wouldn't make much difference in that position. Okay, so the next one is bromine and tetrachlorocarbon. So 1, 2, 3, 4, 5, 6. Hexatriene. Okay, we're just going to do one equivalent here. This time we don't have a nucleophile because that's a solvent. It's very inert solvent. So we do our one, two, three, four, five, our intermediate here, and then bromine nucleophile would come in and generate Br. And what would actually happen is for both of these, you would end up getting another reaction here and here. So this would take it all the way down to hexabromine compound. Okay, and then the last one we have is cyclopentene. Okay, so we have cyclopentene. We have one bromo methyl. So that would be one bromo methyl. After you have your methyl, two methyl, heated in methanol. What kind of reaction would you have? Oh, I forgot my pentene. So it's not put on there, so it would be there. Heated in methanol. So could you have an elimination? Would this be solvolysis? So if you did that, and these would definitely CH2 plus. This is an allylic cation, and they are stable. So you could get definitely that. And what you would get is the nucleophile then coming in and attacking your carbocation. That would be a 1-2 addition. Actually, it wouldn't be a 1-2 addition necessarily. Yeah, let's erase this. Oh, I guess I won't erase that. Okay, so let's just redraw this. Um, so you can get CH2O CH3 coming in from methanol, but you could also get, let's draw our allylic primary. So this is an allylic primary carbocation. This will also, this is an sp2 system. So these electrons can resonate over here. And we draw a resonance arrow. Notice you got a double-headed arrow. It's a resonance arrow. We redraw this structure. And then you got to put the carbocation there. This would be an allylic tertiary carbocation. Which one do you think is more stable? That's right, this is more stable. So this would be a minor product. What would happen then is we got methanol. So methanol would then come in, pyrolysis. This is an SN1 reaction mechanism, and this would be your major product. There you go. Predict the products of the following reaction. Cyclopentadiene. Cyclopentadiene. This looks like a Diels-Alder, so I'm going to make sure I draw my cyclopentadiene with the S-cis-diene, where the orbitals are lined up for my mechanism drawing. CH2, CO, O, CH3, good electron withdrawing group, so this is a good dienophile. And then this is a concerted, where these pi electrons will go to that carbon. These pi electrons will make the pi bond. These pi electrons will go to that carbon. And then we redraw this. I'm just going to go ahead and draw my six-membered ring with my alkene there, my new sigma bonds formed right here. And I don't have to worry about stereochemistry because this is a CH2. So I can just draw this as CO2CH3. And then I'm not going to forget about my bridgehead right there to those two carbons. And that's my Diels-Alder adduct. All right, our next one is 1,3-cyclohexadiene. So that's a six-membered ring. 1, 2, 3, and hexine. So this is our 3. 2 dione electron withdrawing group. 1, 2, 3. 4, 5, 6. So there's 6. This is a straight geometry. And alkynes, they have good electron withdrawing groups here. Dione means this is a ketone. Ine means it's a triple bond. We have 6 carbons. And it's on the 2 and the 5. So we've drawn that correctly. Alkynes can also be dienophiles in Diels-Alder reaction. So these pi electrons are going to go with that carbon. Those are going to go there. It's going to go towards that carbon. So we redraw our six-membered ring. And we're going to draw our new pi bond. It's our new sigma bond. And now we also have to get this one in here because it was a triple bond, so that's still available. Let's go ahead and get our ketones in there. So there's 3, that was 4, CH3, CH3, and then don't forget about our bridgehead, and this time we have 2 carbons. There's our little bridgehead, and that is our product, our Diels-Alder product. Okay, for each structure, draw all the important resonance forms and circle a major. Okay, so the first one is an allylic secondary carbocation, and that's an sp2, sp2, sp2. The electrons can travel through these unhybridized p orbitals. Notice we have our double-headed arrow, and so now it went from there to there. And so this is a secondary allylic carbocation, and this is a primary allylic carbocation. Which one do you think is more stable? The major contributor. Yes, I would circle the secondary. All right, so the next one we have, let's keep with the black. Okay, we have another allylic cation, carbocation, and this is primary once again, but it's sp2 because it's carbocation. This is sp2, sp2, sp2. So the electrons for your resonance structures can travel through those unhybridized p orbitals, and now once that double bond leaves, it gives us here. This is a secondary allylic carbocation. Which one do you think is more stable, primary or secondary? So yes, secondary. Okay, the next compound we have, we will be getting into these. We get into enolate chemistry in chapter 20 maybe. So you have an anion here, and this anion then, so this is sp2, this is sp2, this is sp2. So those electrons can all go through there. And now you have CH2 double bond carbon, oxygen minus CH3. Now, one of the rules for predicting which is your more stable resonance structure would be the charge resonating on your more electronegative atom. So oxygen is more electronegative than having your charge on the carbon. So that would be your more major contributor. Okay, so this compound here, CH3, NH2 plus, O minus. Now, this is sp2, sp2, sp2. So those electrons can travel there. They're going to go from, they always go to the positive, so you want to go from here to there, and then you redraw. And now you have this, and this is actually an amide. We haven't talked about amides yet, and the amide, this would be your more stable because it's a neutral molecule, so that would be your more stable resonance. Now, okay, the next one is this one here, so we will draw this one. Those electrons, no, that should be a positive, so make that a positive. Yes, that should be a positive. So make that correction. Well, you know, if it's not, let's say it's not, let me show you what that would be like. Okay, So basically, those electrons can go right here, right here, and then these, well, okay, those electrons will go right there to make a double bond, and then those will go and make the carboanion there. So what you end up getting is, let's draw your resonance. You draw one of these all at a time. So now you got the negative charge there. And you just redraw everything. This is an aldehyde. And then those electrons will go here to make a double bond. And the double bond will go right there to make a carbon anion. Do your resonance arrows. The reason why this can happen is because they're all sp2 hybridized systems. And so you just keep going until each one of the sp2 carbons gets the turn. So this goes here, and this goes there. Let's see, double bond there, double bond there, double bond there, oxygen. And which one is the more stable? The major contributor? It would be the one here, where the negative is on the more electronegative atom, as opposed to these carbons over here. Okay. Now we're working on this problem here. Let's redraw. CH2. Looks like it's going to be an allylic carbocation. This is a primary allylic carbocation. We do our double-headed arrow, and the electrons push down from oxygen because this is your sp2 center. sp2, sp2, sp2. Excuse me. Okay, so the electrons go here. These electrons go here. And then we redraw this. We get CH2, double bonded, double bond oxygen, CH3, and then your plus charge comes on the oxygen. So you see how you have a plus charge in the beginning of your molecule, you have to have a plus charge also in your final molecule. Conservation of charge. Once again, your charge is going to be more stable on your electronegative atom, whether it's a positive or a negative. So this is going to be your major contributor. It's going to be your most stable resonance structure. Okay, and let's work on the last one here. Let's redraw this one. Pull that back down. Okay, it's chlorine. Okay, so Cl, chlorine. Chlorine are electronegative. They're more stabilizing. And we got a carb. We have an allylic. This is an allylic carboanion. So let's see what that does. We're looking for sp2 centers, so this is sp2, this is sp2, and this is sp2. So these electrons can go from here to there to on that carbon. So put those electrons there. That's CH2. Yeah, I thought I drew that wrong. This should be CH3. Yes, I know I do that often. I apologize. Okay, now, between these two, I'm going to tell you right now, this is going to be the more stable because you got electron withdrawing groups here. They're going to stabilize that negative charge more so than here because they're both primary allylic carbocations. All right, so the next one, predict the products of the Diels order, include stereochemistry. Okay, so we're going to go here. Now, I know I should go that one. It's going to go back here, and this is going to go here. So when you redraw the first product, draw your six-membered ring. These are your new sigma bonds. That's your new pi bond. And then you draw in your carboxylic acid. That's your first product. Okay, the next one here, we have an alkyne. Goes there. It's going to go here. So let's draw our six-membered ring. And this gets an hydrogen. Well, these are our sigma bonds here. This is our pi bond. We have that hydrogen here, and this is an ester. And don't forget, since this is an alkyne, you still have double bond there. And then you got your bridgehead here, which would be connected here. Should be two carbons there. And that is good. You don't have to worry about the 1, 2, and the 1, 4 endo rule where you form these products unless you have substitution. You have to have substitution on both, or you have to have some kind of substituent. Substituent on both your diene and your dienophile. So this is the only one I see. It's going to be that issue, and we'll deal with that. Okay, for the rest of these, I'm going to write them down here. So this is your best dienophile ever. I mean your best diene. It's a good dienophile too. And I have a bad habit here of just drawing these in space when I do my Diels-Alder. So we are going to rewrite this one. Okay. All right. So we have this goes to there, goes to there, and this goes to there. And let's draw our six-membered ring. Our new sigma bond is here and here. Our new pi bond is here. We have CO2H right there. And then don't forget our bridgehead, which is just one carbon there. Okay, so that's that one. Okay, so this one here, what I would do is just draw it first, as it is, and then we will just check it. So this is an aldehyde, CHO. So this is going to go to that carbon. This is going to go make the pi bond, and this is going to make the sigma bond. So let's go ahead and draw this. Six-membered ring. So our new sigma bonds. Our pi bond. And then since we don't have to worry about relative stereochemistry, we can just draw this as a straight line. And then this is CHO. Now you notice that's a 1, 2, 3. 1, 3 is not allowed. Okay, so this would not be correct. So we're going to have to redo this. And if, let's see, so what we do here then is turn this upside down. So let's turn this upside down. And then we can draw this like this. And then we redraw that. Here's our new sigma bonds. Here's our new pi bond. We draw the O, CH3, and then you have the CHO. Now that's a 1, 2. 1, 2 adduct, and that is allowed. And it's because of this secondary interaction where the aldehyde is going to turn here. Can we get a 1, 4? See if we do that one. So what if we turn the diene let's try to turn the diene. and the dienophile both up. And we got this here. Let me just see what this gives us. And we draw our 6-membered ring, our pi bond, and then we have our OCH3 here, and we have our CHO there, and it's 1,3. I thought that, but I just want to double check. So no 1,3. So the correct one, based on the endo rule, would be this compound here, the 1,2 adduct. Okay, let's go back up here and do E. This one is an S trans, but at room temperature, it can get in the S cis. So 1, 2, 3, 4, 5, 6. So we can get that in there. And let's count 1, 2, 3, 4, 5, 6. So this is in the S cis, because we can rotate around that sigma bond to get in the S cis at room temperature. So it would be a slower reaction. Now notice in your diene O file, you have cis. So this is cis. So when we do this, we will need to make sure we draw those in cis. So let's draw our 6-membered ring with our new pi bond and our sigma bonds. And let's draw these on the same side of the ring, CN, CN, which are nitriles. And then we also have to draw these in. And these are also on the same side. So let's put those back. CH3, CH3. Okay. And then we have this one here. Okay, so when this rotates, so when we draw our diene, this is trans. So this is just like that, because that's trans. But notice that this is cis. So that's cis. This has to be cis. Let's draw the CH3 there. CH3 there. And we reacted with the same dienophile. It's going to put the nitriles cis. And when we do this, we have the concerted mechanism. And we draw our 6-membered ring. And we draw in our bonds here. And make sure we have the nitrile on the same side. Now, the relative stereochemistry here to these guys is trans. So just like here, we drew those cis because they were both on the same side. One of these is going to go up, and one of them is going to go down. And that is the correct stereochemistry for your Diels-Alder reactions. And that is the last reaction. Okay, now this is kind of destructing. So when you look at this, and you look at the 6-membered ring, you have to see that these sigma bonds are new, and this came from a dienophile that was here and here, and this originated, the red originated from a dienophile. So the red, we're going to just write CHO, and these bonds here are new. So we're not even going to put those in. And then we're going to go with the blue. We're going to make those the diene. So the first one, you do your retro arrow, just like that. Okay, so let's try the next one. So in keeping with this is your new sigma bond. And this would be your diene. So drawing your diene, and then don't forget your bridgehead. And then we draw this part, and the sigma bonds came from the double bond, And let's look at our relative stereochemistry. Those are on the opposite side of the new ring, so we got to draw them as trans. Okay, this next one, this new bond, these guys here, obviously since there's still a double bond there, came from a triple bond. Then you just write CO2CH3, and then the diene came from here. So you draw that, these two here, and then you just draw these just like that. Okay, this next molecule, these are your new bonds here, your new sigma bonds. And so let's go ahead and make that. You just draw this here, and notice that the hydrogens are cis, so they came from the cis there. And then the diene will come from here, which is just that. So that would be the retrosynthesis of that compound. Okay, this one. Okay, this right here is your double bond, your dienophile, and the hydrogens are on the same side. So that's cis, and this is a what memory? 1, 2, 3, 4, 5. There's your oxygen. These are your carbonyls. So there's your electron withdrawing group. So there's your dienophile, and we deconstruct this. That came from these sigma bonds here. So your dienophile is, your diene is cyclopentadiene. Can you see that? Okay, let's do the same thing here. This came from, those sigma bonds came from your dienophile there. And your nitrile is on the same side, so we draw it just like that. So there's your dienophile. And then this came from, you've got a 5-membered ring. It came from that right there. Okay, let's do the chlordane. If I am correct, chlordane is lice killer, bed bugs. And because it's bad for the environment, which you'll find that a lot of chlorinated compounds and halogenated compounds don't break down biochemically, so they're very bad for biological life. They get in our water systems. So the EPA has decreased the amount of chlordane that can be used, and in turn, the rise of bed bugs have gone up. So anyway, this came from here, right? So you got the Dills alder. Isn't this interesting? You're all learning how to make lice and bug killer. So here is your dienophile. It's a 1, 2, 3, 4, 5-membered ring. So let's count the 5. Chlorine there, and so that's your diene. And then your dienophile, and then your diene came from a 1, 2, 3, 4, 5-membered ring. And so we have that, and then just get your chlorines on there. So the bridgehead has 2 chlorines. This has a chlorine, that has a chlorine, this has a chlorine. So the only one that doesn't have a chlorine is that one right there. And then you can always check these by working them forward. Okay, this one here, once again, what are the new sigma bonds? The new sigma bonds are right here. And so they came from, you just draw this structure just like that, and there you go. And that would be there, your dienophile. And this reacted with the same guy here. Okay. And that's just a derivative. Get somebody patented and made some money off of it so they can have a me too. Let's make sure I do the retrosynthetic arrow here. We'll do this one here. Okay, so we have these sigma bonds originated from my diene right here. And I notice that my nitriles are cis and trans. So I'm going to draw my dienophile as such. And then I'm going to make my diene, this group here, and I'm going to count how big this system is. So let's start with sulfur. 1, 2, 3, 4, 5, 6. So I have a 6-membered ring here. And I have sulfur, which is sulfone. And then this is that carbon here. That's going to be my bridgehead. My diene comes from these 2 carbons here. So that is the reaction that resulted in that product. All right, and that concludes this problem set on Chapter 15, Conjugated Dienes. You should be able to work those kinds of problems for the exam.